So I turned off the SolidWorks cam, and now we're going to look at the Autodesk HSM works and load simulation model. Hopefully that's not because cam was just running. All right, let's pick a new part. Let's pick a part that is in existence as a new part. So the vertical would be good. All right, so where the some of the CAM packages are going to have automatic feature recognition, others are very straightforward. So I would say the CAM/CAMWorks has a fairly steep learning curve, but once you have it trained in what you want it to do, then it's much quicker. On the other end is we go to HSM. It has all kinds of basic operations in it, but we're applying each of the geometries we have to select, and in certain cases it's easy to miss some things that we would otherwise need to find. Failed to load. Alright, that's interesting. This video is not going anywhere fast. Okay, so we'll pick it from there. I closed SolidWorks and launched it again and loaded HSM. So it's same thing. I don't want to switch them, and apparently I don't want to. Might as well just go ahead and let it restart and clear itself out. All right. So for the CAM, predominantly use the CAM for the milling. It does have a turning module and multi-axis, but the turning does a pretty good job on the externals, and so we might load up the shaft and see what we can pick from it. But Autodesk also has a program called Feature Cam that I've had a lot better results on the turning. So also with the CAMWorks turning. Pretty decent. The solid cam turning. All right, so each of them has their pluses and minuses. It is really we'll have to see what they've done for 2019, but HSM has issues with the internal boring. So for the mill, very few issues, and we're going through the same type of process. We have to give it a stock. And so in this case, since this is not quite as rectangular, I'm going to give it a sketch to work from. And so I will just pick up a corner rectangle. And a lot of times, as I mentioned, if I'm trying to keep the original part pristine, I will open up an assembly and insert this part, and then anything that I draw on it, any of the other information is contained just within that assembly. It doesn't affect the original document. So for the base operations is we're going to tell it there's a new job. It's a relative size box. If it wasn't close to size of what I sketched, then I could pick the sketch. And again, I'm not really telling it additional stock at this point. We can manage it either by cutting the stock over size and then going in some distance. And if I draw it, drew the sketch bigger, we could go in and pick that extruded sketch to pick up the origin from. Right. So in the earlier videos that I had for HSM, one of the issues was that the coordinate system was a little clunky. And so they've done a pretty good job of correcting for it. And now we can go in without creating a coordinate system every time. So if I go to my preference is Z and X axis, then I pick a face that acts as that top plane, a direction for the X axis. And one of my minor annoyances is that we can't tab through those fields. I find myself hitting tab a lot and it doesn't go anywhere, so just have to select through them. And then once I pick that coordinate system, that's establishing, again, the datums of the primary, the secondary, the tertiary, getting our geometry set up that we can start to make that code. So a program name and a comment. All right, so we didn't do too much with work offsets, but again, in CAM, you can set the actual number as a 54 or 55. HSM is kind of like Mastercam in that if you go 0 or 1, it's going to stay at 54. A 2 would go to 55. Keep adding those numbers, 3, 56, on and on. And then depending on how it's written into the post with the newer controllers, when you get past, 128, then it switches over. Actually, you go through 59. The newer controllers pick up the G154 P0 through 99 for another 100 work offsets. So there's a lot of flexibility, and I'm sure there are jobs out there. I just don't want to run the ones that have 100 work offsets. All right, so different ways to make the approach. Once we have a job, then we can start telling it what operations we want. So in this case, I'm going to probably, based on the size, I'm going to have clamps that would hold this down, and then we would stop and change the clamps. That's a little bit more intricate than what I want to do, so we'll take the easy, go all the way around. And so a 2D milling, 2D contour, and then we have a library set. And a lot of times we'll go through and add. There is a lot more turned on than we really need. So the holders, inch, brass, copper, we don't need all of the sample libraries, and a lot of the times I will add that to my libraries so I don't have to keep going back to. So flat end mill with, let's just go with a 1/2 inch flat. I'm not sure exactly what I'm selecting, but I'll find out here in a second. So 6400 or 7600 for aluminum plate is okay. For, we never really got down to the point of materials, but if this was a piece of mild steel, we're running a little fast. We're going to see sparks. So that would drop down to probably 3,000, 3,200 on the RPM for steel. Surface feet per minute and cutting feed rate. Oh, and it did stay over in millimeters, so that's maybe not too far off. So let's see if it'll switch. Oh, one contour. So let's pick the base, and we'll come back to that in a second if it'll switch over. And we'll go back. All right, so surface feet per minute, 1,000 surface feet. 92 inches a minute is a little aggressive. All right, if we have the tool geometry, we have plenty of coolant, maybe, but more than likely I would be running that between 40 and 60, and 60 only after I've proved it, and I'm sure I'm not going to yank the part off of the fixture. So we'll leave it for now. We have the options for the coolant, for mist, and through spindle. Turn those on and off. Again, with the contour and the edges, if I only wanted to pick part of this to walk around, I would turn off tangent propagation and propagation along Z so that I could pick just the geometries that I wanted. And clearance planes, stock heights, sometimes these can get a little interesting, so we want to pay attention to the graphic. And so the retract height is kind of this amber, and then the feed height is the I guess that's a little bit more green, and then blue is the top, and the shaded is where it's actually going to create the cutting plane. Right, and then in computer, in control. So in computer is without compensation. In control is compensation, and you're telling it what the diameter is in the register, so basically tool center line. And where is offset, and then it's invoking the G41, G42. And then off inverse where, that one always confuses me, is in the control without compensation, I believe. Anyway, off, and then is right down tool center line. So I stay with in computer or where, so that if I put a value in for compensation, it's basically treating it as 0. And even some of these corners, it's going to be able to pick up. So I know there was a definition. There it is. Inverse where, just like where option, except the where adjustment is entered as a positive number. Okay, so positive instead of negative. Yeah, that still doesn't help. I don't use that one enough to be able to work it. So one of the interesting things about HSM is on its ramp, it has kind of a vertical arc. So it actually switches the code to G18 or from G17 to G18 or G19 and performs an arc lead-in, which can be beneficial, but sometimes on some controls, it also creates a little bit of a not sure what it's doing. All right. And so since my plunge and retract are interior to the part, that tells me that I did not catch the direction of the cut. So we edit, we come back and reverse. I can see the arrow outside of the part now, so that will help. And then it updates and we see the tool path. And other than that being right on the stock, that's not too bad of a location. If I made an adjustment on the lead-ins, we could get away with that. So let's do an adaptive clearing. So 2D adaptive clearing with the half-inch tool. Still a little aggressive there. And let's go ahead and punch it through. We're machining the cavities. And direction, the heights, the 0 and the bottom all look good. So the load, since this is going to be fully engaged in the part, so I think we're at 590. I'm going to take the half-inch tool and I'm going to engage it the full 590 deep. I don't want to be that aggressive on the step overs, and we probably won't need to go both ways. Stock to leave, let's go 10 thousandths in X, nothing in Z, so nothing on the floor. And then there should be a ramp and 2 degrees, so let's go ahead and see what we get. All right, so the advantage of the adaptive, and it's not quite at a torquedo cut, although it has some interesting moves as it comes around the ramp to clean up, is that this is going to be fairly constant load engagement. So when we start thinking about perpendicularity and concentricity, that tool deflection that we would typically encounter, because the tool load is staying relatively consistent throughout the entire tool path, then we're not increasing the amount of wear. We're using more of the flute. So instead of running the last 1/8 of an inch of flute and having it a little bit smaller, and then it gets a little bit bigger as it gets into the less used areas of the flute, we're going to be able to try to stay a little more consistent on those geometries. Right, and then let's see, let's just do a drill operation. So we'd go through and we'd pick for the edge, we'd pick up for the drills, and open up the pocket and the bore, and then this has the end holes, so we'd set up another job setup on the end face so that we could drill and tap, and we'd have to figure out, what kind of angle plate are we going to use? Is this going to be enough contact surface that we're not going to rock over and lose our positional, mainly positional tolerance back to A, controlling perpendicularity to a certain extent, that we'd be able to maintain that geometry. Right, so the base, not so much of an issue. I could put a coordinate system on that corner, drill and tap for the M6, and have a desired result. All right, so where the previous found most of our geometry, this we're going through and we're picking, and so I need any drill, and I think we cleared that for M6. So I don't remember the exact call out. We need a little bit bigger. All right, get past the O and then past the millimeters. Got to the 225, a 240. It's still real small. So all of those libraries that are turned on, we need to turn some of those libraries off. All right, so we're up to a 246D drill. We'll go with the 1/4-inch drill. And then when I pick, I'm going to pick for the same diameter. All right, and then one of the selections, one of the things we want to be concerned with is, am I going to rapid around the bottom of the pocket and keep a minimal retract plane, or am I going to be safe and have all the rapids occur above the part? So if this was a high production, every second counts, then yeah, I would probably wrap it up just enough to clear and risk breaking the tool. Otherwise, we're going to come completely above surface and then walk around. We can do that with the clearances and the heights by making different selections. So if I were to say the feed height was not the same as the top, but from this face, I could change that that retraction to, well, we'll see, to be just above. So in this case, instead of rapiding around the bottom of the part, it would still rapid clear, but then it rapids to 100,000. So that is an aggressive, would say an aggressive program, and even more aggressive is to set the clearance subsurface. All right, so we still want to be safe and go through the process of proving out these programs and verifying they're giving us the right results. All right, so let's go ahead and post one. And so in this case, we have the vertical. It picked up. Let's see. I do not have a post. Let's see, configurations. All right, so I'm not sure where that's pointed to. Anyway, we need the post file so that I can output the file, so we're going to have to find that one real quick. Okay, so we jumped over to Windows. We navigated to the program files to point it. Now I have a little more in the list. I'm not sure what configurations was pulling. And I might have been on the search text anyway. All right, so we're going to do Haas. So we have an A-axis, so that's assuming that there's a some type of rotary. Not sure which that one is. So one of the nice things about the HSM posts is that what is it? It's based on Java or JavaScript? Java. So it's not too terrible to go in and make minor adjustments to the code. So Autodesk has the HSM editor, has the color text, and as we go through, you're going to be able to see preview of the text and what's being outputted. On that post, we don't necessarily have to put out the sequence numbers. A lot of times I'll leave the sequence numbers out because we're dealing with controls that have smaller memories, and I don't need that extra information in most cases. All right, so once it's posted, we can do the simulation as well. So let's go with a stock simulation, and then it's going to look pretty much the same. That it goes through, it makes the cuts, it does the operations. One of the things that all of the simulators are going to do is look for collisions, tell you if something is going to collide. All right.